Let's talk about exponential growth. Exponential growth equations have the following form. Y of t equals c e to the kt, and here c represents some constant, which we'll talk more about in a few minutes, and then k, which we'll call the rate constant, is greater than 0 for growth, for exponential growth. Okay, so for example, in this equation, y just represents some quantity, and it's a function of t. Typically, t represents time in these exponential growth equations. So y could be a population, perhaps a population in a town, maybe population of cells in a culture. There are many different applications and things that y could represent. But y represents some quantity that's changing with time, and this ce to the kt is that exponential growth function. So let me just quickly show you a graph of the general shape of this function. So the particular function I've plotted here is y equals 2e to the 0.1t, but all exponential growth functions are going to have this general shape. They might have different y-intercepts, or they may grow faster or be steeper, but they'll all look in general like this. So let's look at a few interesting properties or interesting facts about the exponential growth function. The first thing we want to look at is the growth rate. So the growth rate is just what it sounds like. It's the rate at which this quantity is growing with time. So if we maybe want to think about a population as an example, just the rate that the population is growing with time. So the way we would find this growth rate is by looking at dy dt, right? The derivative gives us a rate of change. So if I take the derivative of this expression, y of t, what do I get? Well, I have this constant c out front. That's just a constant, so it's going to stay. And then I need to take the derivative of e to the kt. Well, that should be e to the kt times k because of the chain rule. So if I rearrange this a little bit, I could write it as k times c e to the kt, or k times y, where y is just the original function. So then what we see is that dy dt, the growth rate, equals ky. So once again, if we think about a population as an example, this is saying the rate of change of the population with time equals some constant k times the population. One way we might state that is that the rate of change is proportional to the value. So if the population is larger, the growth rate is going to be larger, or if the population is smaller, the growth rate is going to be smaller. Let's also talk about what's called the relative growth rate. So the relative growth rate is the growth rate divided by the current value of the quantity. So we could write that as y prime of t over y of t, or just in different notation, we could write 1 over y times dy dt. So this is just how the relative growth rate is defined. So for example, if y is a population, the relative growth rate is the fraction or percentage by which the population grows for each unit of time. So maybe you'd say something like the relative growth rate is 5% per year, or a factor of 1.4 per month. So remember before, we said that for exponential growth functions, that dy dt we could write as k times y. So then we see that the relative growth rate given by 1 over y dy dt equals ky over y, or k. So then what we see is that the relative growth rate is constant for an exponential growth model. I just want to point out one more thing about this exponential growth equation, and that's about the initial value. So let's note that at t equals 0, the function value y of 0 is ce to the k times 0, which is ce to the 0, which is c times 1, which is just c. So time equals 0 is the starting point, so then we find that c is our initial value of whatever quantity we're talking about. So the initial population, for example. So sometimes you'll also see the notation y of t equals y sub 0 e to the kt, and here they're using y sub 0 to represent the initial value. Last of all, I want to mention an idea called doubling time, which is just what it sounds like. The doubling time is just going to be the time it takes for our quantity y to double in value. So let's see if we can figure out an expression for that doubling time. So I'm going to let t2 represent the time required to double. Then from time equals a to time equals a plus t2, we know that our quantity will double. A way we could write that mathematically is y of a plus t2 equals 2 times y of a. And plugging into our exponential growth function, we could write this as ce to the k times a plus t2 equals 2 times ce to the ka. So let's try to solve for t2, our doubling time. Well, on the left, I could write this as ce, and then in my exponent, distribute the k and have ka plus k t2. And that's going to equal 2ce to the ka. Now, the properties of exponents say on the left that I can split this up, so I could write this as ce to the ka times e to the k t2. And that equals 2ce to the ka. So there's some things in common on both sides that I can cancel. I can cancel the c's, and I can cancel this e to the ka. So I end up with e to the k t2 equals 2. And now I just want to solve for t sub 2. So I can take the natural log of both sides. So the natural log of e to the k t2 equals the natural log of 2. On the left-hand side, then, I'm going to have k t2 equals the natural log of 2. So then my doubling time is a natural log of 2 divided by k, which was my rate constant. And this doubling time is constant for an exponential growth function. Let's look at an example of exponential growth. Here we're told that a certain bacteria has a growth rate of 36% per minute, and that initially the population is 100. We want to do a few things. First of all, we want to write an equation for the number of bacteria at time t. We want to find the amount of time it takes the population to double, and then we want to answer when will the population reach 1 billion. So let's start with part A. We need to write an equation that models the number of bacteria at some time t where t is measured in minutes. Now, in this case, an exponential growth model is going to work well for us because we have this constant growth rate, right, 36% per minute. So if you recall, the way that equation looks, an exponential growth equation, is y of t equals ce to the kt. Now here, c and k are both constants, so basically what we need to do is just figure out what those constants are for this particular situation, and then we will have our equation. So let's start by using this piece of information that initially the population is 100. Okay, so how do we use that? Well, initially the population is 100 means that y of 0, right, so the population at time 0 equals 100. Okay, so then if I plug in 0 for t, I'm going to have 100 equals ce to the k times 0. So that gives me 100 equals ce to the 0. E to the 0 is just 1, so I get that 100 equals c. Okay, so now I know a little bit more about my equation. I know that y of t equals 100 e to the kt. Now, some of you may have remembered the fact that c represents the initial value of the population. And if you remember that, you can just go ahead and plug that 100 straight in. But if you forget that that's what c represents, this process I did here is how you could get to the same point of having this c equals 100. Okay, so then the next thing I need to do is to figure out what k is. And this is slightly more challenging. So k is my rate constant. So we're told that the growth rate is 36% per minute. So somehow we need to use that piece of information to find k. So what I really need is I just need some point on this function, right? I need to know the population at some point in time, right? Because then I could plug in a y value and plug in a t value, and then I would be able to solve for k. So let's try to find the population then at some point in time so we can proceed. So we know that at time equals 0, there's 100 bacteria. All right, that's just our initial value. So let's try to see if we could figure out how many bacteria there are at time equals 1 minute, using the fact that the growth rate is 36%. Well, if the growth rate is 36%, it means that after 1 minute, there's going to be 100 plus 36% times 100 bacteria. Okay, so that's 100 plus 36, so 136 bacteria. So after 1 minute then, there is 136 bacteria, and we can just plug in that point. Okay, so my population then is 136. And then I have equals 100 e, k is what I'm trying to solve for, and time is 1 minute. So now I just solve for k. So if I divide both sides by 100, I get 1.36 equals e to the k. To solve for k, I'm going to take the natural log of both sides, and I'm going to end up with k equals a natural log of 1.36. Now, as a decimal, that's an approximately 0.31, but I'm going to get more exact values if I use this exact value for k, the natural log of 1.36. So then now we can write our final growth function. Y of t equals 100 e, and then k is the natural log of 1.36 times t. So for any time in minutes that I plug into this equation, it's going to give me the population of bacteria at that time. Let's move on to part B, which is to find the doubling time. Now there's a certain equation for doubling time actually. So the doubling time, if you recall, is the natural log of 2 over k. So if you remember this equation, you can just plug your k right in and get the doubling time. But let's say that you forget the equation, right? How could you figure this out just using your brain, right, if you forgot the equation? Okay, so the doubling time is, of course, the amount of time it takes the population to double. So we know once again that at our starting point, at time equals 0, the population is 100 bacteria. So then what we could do is we could take our y of t that we just found and plug in a population of 200, right? So I'm going to set this equal to 200, okay, and that equals 100e to the natural log of 1.36 times t, and then I can just solve this relationship for time, and that's going to give me the time where the population is 200, right? So the population is doubled, and then I can find my doubling time. Okay, so if I follow through with this, if I divide both sides by 100 here, I get 2 equals e to the natural log of 1.36 times time. Take the natural log of both sides, right, to get rid of this e on the right. So I get the natural log of 2 equals the natural log of 1.36 times time. Right, so you can see I get back to this formula. So doubling time then is the natural log of 2 divided by the natural log of 1.36, which is approximately, if you evaluate that, 2.25 minutes. And that's going to be constant for all time. So every 2.25 minutes, the population of this bacteria is going to double. So in part C, we're asked to figure out when will the population reach 1 billion. Okay, so we'll need our equation, of course. So that was y of t equals 100 e to the natural log of 1.36 times t. So all I have to do in this case is just plug in a population of 1 billion and then solve for the associated time. So I'm going to plug in 1 billion for y, like so, and then just solve this relationship for time. So to do that, I'm going to start by dividing both sides by 100. And if I do that, I'm going to get 10 million equals e to the natural log of 1.36 times t. And now to isolate my t, I'm going to take the natural log of both sides. So I'm going to get the natural log of 10 million. On the right, taking the natural log is going to cancel out that e. So I'm just going to be left with the natural log of 1.36 times t. And so I get then t equals the natural log of 10 million over the natural log of 1.36. Which is approximately 52.4 minutes. So it does not take our population of bacteria that long to reach 1 billion. In this example, we're told that between 2005 and 2010, the average rate of inflation was about 3% per year. If a gallon of milk costs $2 in 2005, what will it cost in 2020, assuming the inflation rate remains constant? And then we'll also assume that there are no other factors coming into play here, like half the cows don't die off or something like that. Okay, so this scenario is going to be a good candidate for using an exponential growth model because I have this constant rate of growth, right? This 3% growth rate or average rate of inflation, and that's constant, we're assuming between 2005 and then into the future. So then our equation is going to have the form y of t equals c e to the kt. And here y, in our case, is going to represent the cost of a gallon of milk. And T is going to represent time in years. So then to come up with our equation, what we need to do is we need to figure out what C is, and we need to figure out what K is. So let's start with C. So let's let 2005 be our starting point. So 2005 will represent a time of 0, since we're starting with $2 a gallon in 2005. So then we know that cost is $2 when time equals 0. So I can set up this equation here, plug in 0 for time, and then I can solve for C. So I end up, if I solve this, with 2 equals C, right? Because e to the 0 is just 1. So then I know that y of t equals 2 times e to the kt. And my next step is going to be to solve for k, the rate constant. Now to solve for k, I need another data point. Right? Basically, I need to plug in some cost for y and some time for t, and then solve for k. So let's see if we can figure out the cost perhaps in 2006. So we know then that the cost should have grown by 3%. Okay, so then that means the milk should cost $2 plus whatever 3% of $2 is. So if you work that out, that should give you $2.06. Okay, so now I have a point on my curve that I can plug in here. So know that the cost is $2.06, and that's after 1 year, right? That was in 2006. So I'm going to plug in 1 for time. So then I end up with 2.06 equals 2 times e to the k. So I'm going to divide both sides by 2. And that's going to give me 1.03 equals e to the k. So if I solve for k, I'm going to get the natural log of 1.03. So now I can finish filling in my equation. So y of t equals 2e, and then in my exponent I have the natural log of 1.03 times t. So if I plug in t, which are the number of years after 2005, this is going to give me the cost of a gallon of milk in that year. So t is the number of years after 2005. Okay, so what are we actually asked to find? We're asked to find what a gallon of milk will cost in 2020. So then all I have to do is just plug in the appropriate t value. So in 2020, time is going to equal 15 years. So then I'm evaluating y of 15. So 2e to the natural log of 1.03 times 15. And that equals approximately $3.12. Okay, so that's about how much we can expect a gallon of milk to cost in the year 2020, assuming that the inflation rate remains constant.